Howdy, folks. This is a video with some sample free response questions for you from Unit 3, which is on normal distributions. There's a couple in here that deal specifically with the standard normal distribution and doing z-score type calculations, and then a couple others that deal more with the percentiles and cumulative relative frequency graphs and all that fun stuff. Okay, so let's go ahead and jump into it. So in this first question, we're talking about a company that is considering two different quality control plans. So their first quality control plans will reject batteries as defective, right? Meaning they don't match the general pattern if the weight of the battery is more than 2 standard deviations below a particular mean. And Plan B will reject a battery if the weight falls more than 1.5 IQRs, interquartile range is below the lower quartile. So meaning it's like a lower outlier, okay? Right? So part A says, what proportion of batteries will be rejected with Plan A? So I gave you a hint there, which was to sketch the normal curve, okay? They didn't tell us a mean or a standard deviation, but I'm still going to mark it here. So I have my mean and my standard deviation. And Plan A says that we will reject any battery if it falls more than 2 standard deviations below the mean. Okay, so meaning here's my cutoff. I'm 2 standard deviations below here, and I'm going to reject all of this area here. Okay, and I also give you a hint that z equals 2 means that you are 2 standard deviations above the mean. So this value is like z equals -2, right? Because remember, no matter what the mean or the standard deviation is, you can convert it to a z-score, right? Wherein you will get these z values. So z is -2 here. So if you remember from the empirical rule, that's the 68, 95, 99.7 rule, okay? Remember that 95% of the data falls within 2 standard deviations, right? So from here, let's say here's 2 standard deviations. So from here to here is 95% of my data, which means each of my tails must have 2.5% of the data. Okay, so the proportion of batteries that would be rejected, so I'm finding here the probability that z is less than -2. Oops, I really should write this a little bit differently. Hold on, because I know when I write, my z's look a little bit like 2. So z is less than -2. That probability is 0.025. Right? So you can write it like this as a decimal, or you can write it as a percentage, 2.5%. Okay? All right. Then part B says, what proportion of batteries will be rejected by Plan B? Okay. So again, I'm going to go ahead and draw my normal curve here. Hopefully better than the first one I did, because that one was atrocious. Okay, I still have my mean in the middle and my standard deviation. And it says we're going to reject the value that is 1.5 IQRs below the lower quartile. Okay, so here, right, let's say I'm going to do a couple of marks on here. So let's say Q1 is here, Q3 is here. So I need to figure out what this distance is. I need to figure out what the IQR is, right? That's my IQR. I'm going to multiply that by 1.5 and then subtract that distance from Q1 to get a cutoff point, right? So I have to figure out what my cutoff value is. So this value here, this red line here, is Q1 minus 1.5 IQR. Okay, and I'm going to reject any battery that's below that. Okay, so I gave you a couple of hints here. The first was to find the Z values that capture the middle 50% of the data. Okay, and I can tell you from looking at the Z table, right, that I know that these quartiles in Z scores are Z equals negative 0.67 and Z equals positive 0.67, okay, which you'll be able to see if you look at an actual Z table, right? So you would look for, this is the Z value associated with the area of 0.25, right? And this is the Z value associated with 0.75 as the area. Okay, so that means my IQR for my Z-scores is 0.67 minus negative 0.67. And remember, it doesn't really matter what the mean and standard deviation are because they told me it was a normal distribution, so I can figure out, I can just use Z-scores, right? Because even if they told me the mean and the standard deviation, really, when I would do this, I would convert it to Z-scores anyway, right? The proportion or the probability is not going to change whether you're dealing with your standard normal with Z-scores or if you're dealing with another normal distribution that has, that has X values and has a different mean and standard deviation. Okay, so my IQR here is 1.34. 1.5 times my IQR is 2.01. Now, if you're doing this on a calculator, you may have gotten slightly different decimal values than I did, right? Like if you figured out what the Z value was, these Z values down here, if you figured out what these Z values were, using the calculator rather than using the Z table, you'll get a slightly different answer, but it's very, very small. Like the difference is not so much to be substantial, right? Okay, so now I know my lower bound, my lower outlier bound is Q1, which is negative 0.67, minus 1.5 times IQR, which is 2.01. So you get negative 2.68. So you then have to use the Z table to figure out what's the probability that I get a Z value that's less than negative 2.68. Okay, and when you either plug that into your calculator or you look at the Z table, you get 0.0037. Okay, and like I said, you can leave this as a decimal or you can write it as a percentage, which is 0.37%. Okay, so you're much more likely to reject a battery using plan A than you were to reject a battery using plan B. All right, so give me a sec to clear my screen off and then we're going to look at another FRQ. All right, y'all, so here is our next FRQ. This one deals with a cumulative relative frequency graph. So all of these questions are going to be more about cumulative relative frequency and percentiles. Okay, so essentially what this is in this scenario, in this problem, that we're dealing with a real estate company, right? And they're dealing with they're tracking all of their agents' sales volume, okay, meaning how much they sold in a month, right? So, for example, right, this point right here, right, which is at a 0.6 for cumulative relative frequency, that means that 60% of the 60% of their sales agents sold $500,000 or less, right? Or you could say that another way you can think about this is that 500,000 is the in sales is the at the 60th percentile for their agents. Okay, so this first question, this first part says, in the context of this question, explain what information is conveyed by the circled point, which is this point right here. So essentially what they're asking you to do here is interpret the percentile. Okay, that's basically what they're asking you to do here. So that point is at the 40th percentile, and the X value associated with is 300,000. So the way I would write this is I would say this point indicates that 40% of sales agents had sales volume of $300,000 or less in the month shown here. Okay, all right. Another way you could have said that is that you could have said something along the lines of $300,000 is the 40th percentile of monthly sales, right? And then you would really have to go into a little bit more detail and make sure that you write exactly what a percentile is. So then you would have to then interpret the percentile in context. Okay, so you could have added this sentence right here at the start of your little explanation here, but you didn't have to. Okay. All right, part B says, what proportion of sales agents achieved monthly sales volumes between 700 and 800,000? So I'm looking at 700,000 and 800,000. So I want to look at their percentiles. So their percentiles were 0.7 and 0.8. Okay, so when they're asking here about proportion, they're asking you about essentially you have to subtract percentiles. Okay, so if I was to answer this question, I would say 80% of agents had sales volume of $800,000 or less, and 70% of agents had a sales volume of $700,000 or less. Okay, so that means that 0.8 minus 0.7, which is 0.1, or you could write it as 10% of agents achieved monthly sales volumes between 700 and $800,000. Okay, it's that simple. The only math you had to show was this, doing the subtraction. Okay. All right, so then part C says, for values between 10 and 11, the cumulative relative frequency plot is flat, which is true. Okay, if you look between 10 and 11, there is no change there, okay, which means that the percentile is unchanged. Okay, that's what that means. So they're asking, in the context of this question, what does that mean? Well, what that means is that if there was no change between 10 and 11, then that means there were no extra people, right, that made that much, like that made between 10,000 or a million and 1100,000 or 1.1 million dollars, right? So in the context of this question, it's just that there were no agents whose monthly sales volume was between 1 million, a million, and 1.1 million. Okay, right? Because if there were people that made between a million and 1.1 million, there would have been a slight increase, right? Because remember, cumulative relative frequency is all based on the number of people in each category, right? Or at each level, basically. So if it doesn't go up at all, that means there was no change or no one between those two values. Okay. All right, part D, the last part here says a bonus is to be given to 20% of the sales agents. Those who achieve the highest monthly sales during the preceding month will receive a bonus. So this is asking, what's the minimum monthly sales volume that an agent has to achieve, okay, to qualify for the bonus. Okay, so if essentially we're dealing with the top 20% of people, right? So top 20% of agents, that means we have to be at the 80th percentile or above. Okay, so we need to find the monthly sales for the 80th percentile. Okay, so I'm going to go back up to my graph here and say, well, the 80th percentile is right here, right? So I need the monthly sales volume attached to the 80th percentile, which is 800,000. Okay, so I would say the 80th percentile of monthly sales volume by sales agents in this month is $800,000. So agents must make at least $800,000 to qualify for the bonus. All right, so that is it for this question. Right, so the key thing here, y'all, is make sure that you're careful and you're looking at these graphs carefully. If they're asking you for a proportion, they're asking you usually for a cumulative relative frequency. Okay, if they're asking you for like what the actual X value is, you have to use the percentiles in the cumulative relative frequency to figure out what the X value is associated with that particular percentile. All right. So again, give me a sec to clear my screen off, and then we're going to look at, I've got two more problems for you. The next two are going to deal a little bit more with like the z-scores and calculating percentages from the normal distribution. All right, y'all, so here we are at another free response problem. Okay, so this one is talking about a professional sports team. We're going to deal with some speed data and some weight data and do some z-score calculations and things here. Okay, so we have some data for speed here that the mean is 4.6, standard deviation is 0.15, and the minimum is 4.4. So this question is asking, based on the relationship between mean, standard deviation, and minimum, is it reasonable to assume that this distribution is approximately normal, and to explain why? Okay, so we kind of have to do a little bit of mapping to explain this. So remember, in a standard normal curve, right, you have the mean here, and then you have, right, 3, 2, and 1 standard deviations below, and then the same thing for above, 1, 2, and 3 standard deviations. Okay, so what that means is, in a normal distribution, the minimum will be around here somewhere. Okay, that's where it should be in a normal distribution. So let's see what it would be in this distribution. So my mean was 4.6, right? And then I'm dealing with the minimum, so I'm just going to look at the bottom half of this distribution here. So 1 standard deviation away, right? 1 standard deviation away would be the mean, 4.6, minus the standard deviation, 0.15, okay, which is 4.45, okay? And then I'm going to keep going. So then 2 standard deviations away would be 4.3, and then you have 4.15 here. Now, in this example, the actual minimum is 4.4. So it's like right here. Okay, so from that, we can say, well, no, it's probably not normally distributed. Okay, because the minimum, right, doesn't follow, or it doesn't kind of show up where it's supposed to. So the way that I would write this, okay, is I would say, no, it's not reasonable. Okay, and then what I would do is I would show a z-score calculation for the minimum value. So the z-score for the minimum is 4.4 minus 4.6. All of that divided by 0.15, which is negative 1.33. Okay, so in a normal distribution, the z-score for minimum would be smaller, right? Or would be, or maybe not, smaller is not the best word, would be more negative. Okay. This distribution has no z-scores below negative 1.33, meaning that the distribution is not approximately normal. Okay, right? So I kind of have my explanation written out here, but I've shown a lot of my thought process using the drawing. Okay. All right, so let's look at part B. Now we're dealing with strength here. So we have previous strength data, And from that, I have a mean and a standard deviation for amount lifted. Okay, so this says calculate and interpret the z-score for a player in this position who can lift 370 pounds. All right, so let's calculate that. And I'm going to do it off to the side here. So that z-score would be this is my x value. This is my mean. Okay, so mu. And this is my standard deviation, or theta. So I have 370 minus 310 divided by 25, okay, and that value is 2.4. Okay, so that's my calculation. Then the interpretation is that the z-score of 2.4 indicates that this player can lift, or rather that, rather not that this player, that the amount of weight this player can lift is 2.4 standard deviations above the mean for all other players in this position. Okay, so that's your interpretation, right? Which is just the definition of a z-score, right? 2.4 standard deviation above the mean. And I've included my context, which is really what you need, okay? All right, then last part here, part C, is we're going to compare two players, okay? They only have one spot, and so they're asking which player should the team select if they can only pick two, right? So if we go back to what our original, our original data is here, okay? For speed, right? Obviously, this player is faster, right? Player A is faster. But player B, if you look at the weight data, player B can lift more. So we're trying to figure out who has the advantage here, right? And in order to do that, we have to calculate some z-scores, right? I can't compare how much better of a runner player A is to how much better of a lifter player B is until I standardize all of my scores and I convert them to z-scores. Okay, so for your run, okay, so for running, the z-score for player A is 4.42 minus 4.6, which again, I got from the previous information from the problem, the mean and standard deviation from part A and part B. Okay, so 4.42 minus 4.6 over 0.15. Okay, and that number is, hold on. So when you actually do that calculation, that number is negative 1.2. Okay, the z-score for player B for running is 4.57 minus 4.6 over 0.15. Okay, and that number is negative 0.2. Okay, for the weight, okay, the z-score for player A is 370 minus 310 over 25. So that number is 2.4. The z-score for player B is 375 minus 310 over 25, which is 2.6. Okay, so player A is a much faster runner comparatively to player B, right? So player A is a faster runner, then player B is a better weight lifter, right? The difference between the z-scores for weight is very minimal, whereas the difference in z-scores for running is much larger, okay? So the way that I would kind of write this out and justify this is that z-scores indicate both players are faster than average and lift, and I'm going to say stronger, and lift more weights, right? And stronger than average. Okay. Comparatively, player A is a faster runner. Okay. Right. Player A is a faster runner, and player B is or can lift more weight. Right. Right. But you want to say then that player A, oh, I've run out of writing space. Okay. Sorry, y'all, I've completely run out of writing space. Hold on one second. I have to edit my document so that I have a little bit more space to write. 1 second. All right, apologies, everybody. I kind of messed up my calculations over here, but really what we're looking at right now is the justification. Okay, so player A, so you've talked about the z-scores, you've talked about who's a faster runner and who can lift more weight, and then you have to select one of the two players. So you would say player A is, oops, it's not allowing me to write. Player A is a better choice because player A is a much faster runner than player B, right? A negative 1.2 z-score compared to negative 0.2 z-score, and only oh dear, sorry guys, and only slightly less strong, right? A 2.4 z-score compared to 2.6 z-score. All right, so that would be my justification. Okay, in order to get all of the points for the justification, you had to, essentially what you needed was this last part here, right? That you used the z-scores to, and the adjusted, like the adjusted scores, right? The adjusted stats here in order to accurately compare these two players. All right, y'all, so we've got one more problem here. So give me a sec to clear my screen off, fix a couple of things, and then we'll be right back with one last FRQ. All right, y'all, so here we are. This is our last normal distribution FRQ. Okay, so in this one, we're dealing with and talking about weights of a carton of eggs. Okay, so we're talking about a dozen eggs here. Okay, so they tell us in the problem that the weights of full cartons, right, of 12 eggs each are normally distributed with a mean of 840 grams and a standard deviation of 7.9 grams. Okay, so part A asks, what's the probability that a randomly selected pack of 12, okay, will weigh more than 850 grams? So 850 grams is my X value. Okay. And then my mean and standard deviation are underlined up here. So I'm going to indicate, I'm going to give this a variable here because it didn't give me one. So I'm going to use the variable W for weight. So this is the weight of a full carton. Okay, it's always a good idea if you're going to use a variable that you indicate what that variable is in context, right? Remember, statistics is all about context. The problems have no meaning if you don't give them some connection to something real, to some context, okay? So this variable W has a mean. So the mean of variable W is 840 grams, and the standard deviation of variable W is 7.9 grams, okay? Which is just what they told us in the problem. So I'm not creating anything like out of thin air. This is just what they called it in the problem, and I'm just abbreviating to make my life a little easier. So if I'm trying to find a probability from a normal distribution, I need to calculate a z-score. So my z-score for the weight of 850 grams is 850 minus 840 divided by 7.9. Okay, and that value is 1.27. I rounded a little bit, but you get approximately 1.27. Okay, so then you can either, okay, you have two options. You can either use a z-table here, or you can use normal CDF, right, on the calculator, okay? Because remember, what we were trying to find here, and what I didn't do, which I should have, was sketch the normal distribution curve, okay, where I have 840, my standard deviation was 7.9, okay, and I'm trying to find what's the probability that I get a carton that weighs more than 850. So here's 850, and I want a more probability, right? So that's the area I'm trying to find. So what I'm calculating here is the probability that W, the weight, is greater than 180, or is greater than 850, sorry, which is the same as the probability that Z is greater than 1.27. Okay, you don't have to write both of these, both of my probability notations, but you do need to have one of them, at least one, because that gives the answer some context. So from the z-table, you get the probability that's less than 1.27. So the probability that z is less than 1.27 from the z-table is 0.8980. So if I want to find the greater than probability, that's 1 minus 0.8980. Okay, so my final answer here is, hold on, is 0.1020. Okay. Right, so that's my final answer. Again, you either need to write this probability notation or this probability notation. One of the two. You don't need them both. Okay. All right, so let's look at part B, which is a little bit tricky, but the actual math involved is not too crazy. Okay, so they say the weights of the empty cardboard containers have a mean of 20 and a standard deviation of 1.7. Okay, and they say it's reasonable to assume independence between the weights of the empty cardboard containers and the weights of the eggs, meaning that, like, if I have a slightly heavier cardboard container, that doesn't also mean that I'm going to have slightly heavier eggs, right? One does not affect the other. okay? And then they say it's also reasonable to assume independence among the weights of the 12 eggs, meaning that the weight of one egg is not going to affect the weight of the other egg, okay? So they defined a variable for us here, okay? They said, let X be the weight of one egg, okay? So a single egg. So they want us to find what's the mean and the standard deviation of that random variable, okay? So we have to go back a little bit to what we know about the weights of our cartons from up here. So remember, we defined this variable W as the weight of a carton, right? So the weight of a full carton, okay, is the packaging, the weight of the packaging, which I'm going to call P, right? Plus 12 eggs. Okay, so that's 12 times X, because X is the variable that I gave to one egg. Okay, so remember that we know for mean and standard deviation, when you are calculating a new mean and a new standard deviation, that mean is affected by both addition and subtraction, as well as multiplication and division. Okay, so the mean then of the weight of the full carton is the mean of the packaging plus 12 times the mean of the eggs, right? I know this value from part A, and I know this value from part B, right? They told it to me at the top, right? So the mean of a full carton, right? Like eggs and packaging included, remember, was 840 grams. Okay, the mean of the packaging was 20 grams. And then I have plus 12 times the mean of one egg. Remember, so this is what I don't know. That's what I'm trying to find. It's the mean of one egg. Okay, so I just have to solve this equation for this, the mean of one egg. So the mean of one egg is 840 minus 20 divided by 12. Okay, and that value is 68.33 grams if you round. Okay. All right. Okay, so for part two here, right, it says what's the standard deviation of one egg, right, of this distribution of one eggs, okay? If you recall, when we talked about combining and multiplying, dividing, adding, subtracting constants to standard deviations, remember, we would never deal with standard deviations. You want to deal with variances, right? So we never add really or multiply with standard deviations. You have to use variances. Okay, because what we're actually doing here, okay, right, in our fanciful equation that we wrote right here, okay, really what we're doing here is we're adding a bunch of variables, right? We're adding different normally distributed variables, right? We have the packaging and the eggs, right? Those are two individual distributions, two individual normal distributions that we are adding together, that we are combining, right? So we can't add standard deviations. We have to deal with variances, right? So the variance of the whole carton is equal to the variance of the packaging, right? Plus 12 times the variance of one egg. Okay. All right. So we know from part A, again, we know from part A, we know the standard deviation. We know the standard deviation. And then same thing here, we know the standard deviation. So the variance of W is the standard deviation, 7.9 squared, okay, which is, oh, hold on. Okay, so that value is 62.41. Okay, my standard deviation for the packaging was 1.7. So the variance is 1.7 squared, right? And that value is 2.89. Okay, and then this, again, is my unknown. That's what I don't know. Okay, so I can now kind of plug in the information that I know and do some solving here. All right, so I'm going to put all this together and say, okay, 62.41 equals 2.89 plus 12 times the variance of one egg, which is what I don't know. So the variance of one egg is 62.41 minus 2.89 divided by 12, which is 4.96. So that means that the standard deviation is the square root of variance. So square root of 4.96, which is approximately 2.23, pardon me. And I did all this in a calculator beforehand, right? 2.23 grams, okay? Right. So the key thing for this one is we had to write an equation for what actually made up a carton of eggs, right? It was made up of the packaging and the individual eggs. Since there's some variation in both the weight of the packaging and the weight of the individual eggs, right? You have to use both of those ideas, right, and both of those elements in order to figure out what the mean and standard deviation would be of just one egg, right? And then another key thing that we have to remember here, right, is that you can't figure this out, the standard deviation part, you can't figure that out the same way that you did with the mean part, right? With mean, you can just plug the information that you know, like the means that you know, into our lovely equation for the weight of a full carton, right? But because we're combining different variables, you can't do that with standard deviations, right? but you can do it with variances, right? So you had to take the standard deviations, square them first to figure out what the variances were. Then you could plug them into the equation, because variances you can manipulate, standard deviations you can't, right? Then once you know the variance, you take the square root of it to figure out what the standard deviation is. All right, y'all. So that is it for these practice problems for normal distributions. I hope these helped you and kind of helped you work out a little bit more how to do these types of problems. So I will see you in the next video. Bye, y'all.